Okay, hello everyone, welcome back to our episode 16 for the number series. For today's video, we will be doing the exercises about Pythagoras triangles. The key takeaway for this chapter is all of the fundamental Pythagorean triangle could be expressed as the form of these, where m and n are not both odd numbers and they don't share any factors. And for other non-fundamentals, you just multiply those a, b, c by some kind of factor, and that's how you get any non-fundamental triangles. And let's begin. So there are 11 non-fundamental Pythagorean triangles with hypotenuse less than 50 and find them. And this 3, 4, 5, this ratio is going to produce 8 different non-fundamental Pythagorean triangle, and 8, 15, 17, they're going to produce one extra non-fundamental triangle, and 5, 12, 13 is going to produce 2 different Pythagorean fundamental triangle. And question 2. Find the fundamental Pythagorean triangle with hypotenuse 265. So this is just an example, and we know that 265 could be expressed as sum of 2 squares, and you're gonna find out in the chapter 18 about why that's going to be the case, because it has no factor that's congruent to 3 modulo 4, 2, and odd power, and that's why it can always be represented as a sum of 2 squares. And question 3, find the fundamental Pythagorean triangle with leg 100. So I just suppose a equals to 100, and I just take a solution pair for m and n, and I use it to solve b and c, and I check that it does work. It is a right triangle. And question 4, how many Pythagorean triangle, fundamental or not, can you find with hypotenuse 1105? So those are the fundamentals. Well, you just try to expressing 1105 using 2 different squares, and you get m and n. You calculate the other 2 sides, and for the non-fundamentals, you just finding all the divisor of 1105 and represent them using sum of 2 squares and find the other 2 sides, and each one of the unique fundamental triangle is going to produce a different non-fundamental Pythagorean triangle, and in total there should be 4 fundamental and 9 non-fundamental. Question 5, for AB to share a factor of D, a squared plus b squared equals to c squared, show that AC, the greatest common divisor of AC equals to greatest common divisor of BC equals to D. Well, we do know that C also have a divisor as D, because we can factor out D, and this is definitely going to be an integer, and D is going to be an integer, and this thing should be a square because this is a square. So D is going to be a divisor of C. If BC do share any larger factor, and then AB is going to share a larger factor than D, so that's not going to be the case. So the D is the greatest common divisor of B and C. Question 6. So for AB don't share any factors, AB equals to C to the power of n, show that AB are n's power. So we do know that each prime factor e to the power of n either belongs to A or B, because they can share that prime factor at the same time, because A the greatest common divisor of AB equals to 1. Therefore, so each prime factor to the power of n or its multiple is going to belongs to exactly one of AB. That's why A and B, they are going to both be n's power. And the 7 show that if A and B, they do share some kind of factor, A and B, they are not necessarily the n's power. So let's take this as an example. For example, c to the power of n equals to 2 to the power of n, and a, b, they share a factor of 2. And after you divide each one of them by a factor of 2, we're gonna find that b is not to the power of n. And we make our contradiction. And question 8, this dude find a right triangle whose area is numerically equals to the length of its hypotenuse. Show that this cannot happen if the triangle has integer size. So this is what we get based on the triangle we draw here. And after you done a little bit of factoring, we got this. And since a, b, they are integers, so we just need to try the first few small values, and we get all of the possible value of factor in form like this. And we find that none of them fit because they all have a factor that doesn't belong to 16. So therefore a and b, they can't be integer, and such triangle couldn't exist with integer size. And question 9, in all Pythagorean triangle in the table in the text, one side is a multiple of 5. Is this true for all Pythagorean triangles? In fact, it is, because if n is a divisor, is a multiple of 5, then a is going to be multiple of 5. If n and m, they are congruent to each other, then b is going to be multiple of 5. If n and m, they don't congruent to each other, well, c is going to be multiple of 5 because, well, we know that ab, we know that mn, they cannot be multiple of 5, and they either congruent to 1 or 4, and they don't congruent to each other. That means 1 is congruent to 4 and 1 congruent to 1. And adding that up is going to have a multiple of 5 for the length c. Therefore, this is always going to be one side that to be a multiple of 4. No, multiple of 5. And question 10 shows that 12 divides the product of legs of a Pythagorean triangle. So first we're gonna find that it always has a factor of 3, because if m or n, they are congruent to 3, then it's definitely going to be true. Or none of them is congruent to 3. This one, any square is going to be in form of 3k plus 1. They are congruent to 1. And this thing is going to be multiple of 3. And similarly for the factor of 4, if either of them are multiple of 2, this thing is going to be multiple of 4. If none of them is multiple of 2, they're gonna congruent to 1, and this is going to be multiple of 2, and the whole thing is going to be a multiple of 4. And question 11 shows that 60 divides the product of sides of a Pythagorean triangle. While using the conclusion from 9 and 10, we know that 12 divides the product of the leg, and one of the sides is always going to be the multiple of 5. Therefore, 60 is going to be a divisor of the product of 3 sides. Question 12. Okay, this is a quadrilateral, not a parallelogram. So with integer size and integer area, what is its area? So this is basically two Pythagorean triangle with the same hypotenuse. They combine together, and we just have to calculate each area of triangle separately, and we sum them up. Is going to give us the area of this quadrilateral. And so for the answer of part A is going to be 234. Show that such quadrilateral triangle are not common. Can you find another one? Well, it's not that uncommon, you know. You can find like 1 million more according to the part C. So you just need to find you just can like find any fundamental Pythagorean triangles and find the least common multiple of the hypotenuse, and we times each triangle with the least common multiple, and it's kind of hard to express it, so we're gonna find the least common multiple of those two numbers, and let's say this one is going to be 65, and then we multiply this by 13 and multiply this whole thing by 5. It's going to give us a triangle that has the hypotenuse of 65, and yeah, and we can fuse those two triangles together. It's going to give us a quadrilateral triangle as they ask. And part C, yes, definitely, because, well, this is not that uncommon, and you can just pick any non-fundamental triangles and fuse them together by finding the least common multiple. And question 13, find that all fundamental Pythagorean triangle whose area are twice of their perimeters. And this is what we given, and doing a little bit factor, we got this, and we're gonna test each possible value of n. And it has to be a divisor of 4 because mn, they are integers, and we find that n equals to 4, m equals to 5 are only solution because we are looking for mn, they don't share any factors, and also they are not both going to be odd. Therefore, this is the only Pythagorean triangle we can find. And the next question is just very similarly. Instead, we are just having 3 times of its area. Well, and we are just going to follow a similar process, and we find that this is what we get, and we try the value of n, and we find the value of mn. And question 15, show that 3, 4, 5 are the only solution of x squared plus y squared equals to z squared. And assuming that the middle number is a, and the number to the right is a plus 1, to the left is a minus 1, and we solve that, a either equals to 0 or 4. Since a is positive, so a equals to 0 is not valid, so yeah, this is the only consecutive side that form the Pythagorean triangle. Well, question 16 is just very similar. You just replace 1 with the number k, and you're gonna find that a equals to 4k, and a minus k equals to 3k, a plus k equals to 5k. Okay, that's the only form. And question 17, guess the theorem here. But I think this question, part B, is kind of like a spoiler, because yeah, it just give us the result of part A. So, well, this is going to be your conclusion, and we know that 2n plus 1 gives all of the possible value of 2a plus 1, because it must have a form like this. And yeah, for each odd square, we must have a odd square root, and we already included all of the possible value of odd square roots, and we're gonna have all of the odd numbered squares, and that's going to give us all of the possible values, such as those consecutive legs and hypotenuse. So question 18, looking in the table and find two Pythagorean triangles with the same area. And notice that those two pairs, they have the area of 210. Well, part B is going to asking us to find another two pairs. Well, we can just use the non-fundamental and multiply each pair by a factor of 2. We are doubling the area of each triangle, and they are still going to have each. We are just going to double the area of the triangle, and it's not going to affect this equality because two sides are both doubled. Or you can just like brute force to find another pair like Y did first time. It was quite stupid. I should just use the non-fundamental triangle. Okay, part C, prove that two Pythagorean triangles with the same area and equal hypotenuse, they are congruent. So those two are the information we are given, and we rearranging them like a little bit, and we can use the, I don't know, like we are just making the square, and we got those two things together, and we combine them. We find that A either equals to D or equals to E, and yeah, they are kind of corresponding. So we know that to prove they are congruent, three sides that have equal length is enough. So that concludes our proof. Question 19 shows that this is impossible. Well, we just need to take a look at the modulo 2. The right side is congruent to 0 and the left side is congruent to 1. This is impossible. For 20a, we just need to expand them and find that it is indeed true. And for part B, it is very easy to prove that v is integer using the congruence of modulo 2. And to prove this thing is equal, we also just try to expand it and comparing the left and the right side. And how this proves there are infinite many square triangle numbers is that from part A, if we can find the A and A plus 1 squares equals to C squares, we can get the next A and C have such a property. There's a recursive relationship. This is A plus 1, and this is C. And we can get it from this first pairs. And we do know that such pairs exist. So, and yeah, we have infinite this A and C have this kind of expression. And those infinite C and A is going to give us infinite V and U. We already proved that using those expressions, U and V, they are congruent. No, they are equal to each other. And therefore, they are infinite square triangle numbers. And that concludes our section today. And thank you for watching. See you in the next one. Bye bye.